Today we are going to present our paper on LinDistFlow model congestion pricing, bounding the changes in power tariff. In this brief video, we will explain how to implement the results presented in the paper using the software MATLAB. So first, let us consider the power flow model which we use, which is called the LinDistFlow power flow model. Herein, the real power injections given by the vector P and the reactive power injections given by the vector Q are linearly related to the voltages in a power network which is given by the vector V. In MATLAB, we use the software called MATPower in order to get a test case, 4-bus radial distribution network, which can be loaded using the command load case. We can get the from and to buses of each of the 3 lines in the power network, and from there we can create a directed graph using MATLAB's digraph function. Then we can plot the graph so derived. Now we are interested in getting the incidence matrix of this graph, so for the same we use the incidence function in MATLAB. Finally, in order to get the R and X matrices, we use the formula that R equals F times diagonal of the resistance times F transpose, and similarly X has the same formula except we use the diagonal of the inductances. Here F is the inverse of the reduced incidence matrix which we just derived. We now discuss the coding of optimal power flow based on the LinDistFlow model in the MATLAB software called CVX, which is used to solve convex problems. Over here we define the decision variables in CVX, this auxiliary variable which will store the dual variables after solving the problem. We minimize the cost of all generations subject to voltage level constraints, equality constraints for load demands, box constraints which limit the amount of generation available, equality constraints for line flows, and finally a line flow limit. Then we return the optimal dual variables as well as the optimization problem solution. We now discuss the results as we carried out through the simulation. Recall that in the power network there is a line between the slack bus and bus 3 apparent power flow limits and corresponding marginal prices of real power demand at bus 1. The blue line over here denotes the upper bound proposed in our paper, while the red line denotes the actual prices which are calculated through corresponding dual variables. As we can see that the line stops binding at slightly higher than 0.6 per unit of apparent power flow, and at that time both the real as well as the upper bound converge to 0. With this we conclude our talk. Thank you.